Hello, class. Okay, so last time we were talking about circular motion, and yeah, we're going to go over one application of that, which is orbits. So we have one object orbiting around another, and Isaac Newton showed that planetary orbits are actually elliptical, but for our purposes, they're so close to circular that this is a very good approximation to an actual planetary orbit. Kind of interesting that our orbits, like the Earth's orbit, is very close to circular, just a tiny bit elliptical. But we can handle circular orbits in an algebra-based class without too much trouble. But if you try to look at an actual elliptical orbit, the math gets much more complicated. You wouldn't even normally deal with this in a calculus-based class. It would be like a somewhat more advanced class. But our orbits are typically very close to circles, so what we're doing works very well. Okay, so I wrote down a few things off the side. Here's Newton's law of gravity. That's a constant. And we're actually going to consider a special type of orbit where we have one very massive object and one much smaller object. So this could be like the Earth and the Sun, or it could as well be say the Sun and Jupiter. So Jupiter is much more massive than the Earth, but still the Sun is so much more massive than anything else in the solar system that you could consider any planet. Now, technically speaking, the Earth doesn't really orbit around the Sun. What actually happens is the Earth and the Sun are both orbiting around a point called their common center of gravity. So if you just have two objects, they orbit around the center of mass, not center of gravity. And I wrote down the formula here for the center of mass. So let's say we place the Sun at x equals 0. That would be x1 is 0, and x2 would be the, just like the radius of the orbit. And m is, m1 would be the mass of the Sun, m2 would be mass of the planet. In general, you can find, let's just forget the Sun and the Earth. Let's just say we have some, let's call this center of mass. So let's say for this particular system, the center of mass was right here. What you would have is, this picture wouldn't really apply anymore because the orbit of the planet would be centered on this center of mass, and this more massive object would also be orbiting around the center of mass. So the actual picture would look more like this. So, this object would be going in a smaller circle, the lighter object would be going in a bigger circle. Now, if you have two equal masses, the center of mass would be at the midpoint. But when you have one object is more massive, that kind of pulls the center of mass closer to the larger object. And in the case of the Sun and any planet except for Jupiter, the center of mass is inside the Sun. And, when you look at the size of the solar system, even though the Sun is very large, the Sun is just a tiny dot as far as actual physical space is concerned. Like when you compare the radius of the Sun to the radius of an orbit, tiny, tiny fraction. And so, basically what we can say is that the Sun doesn't really move. We can treat the Sun as just being fixed in place, and all of the planets orbit about it. And technically the Sun does go through some motions because it's being tugged on by the other planets, but it's mostly just fixed in place. So with that being said, one more thing I should write down here. We talked about this in the last class, that acceleration for an object moving in a circle, it has an inward acceleration equal to v squared over r. So again, let's go back to the sun, which is basically fixed in place, and a planet with a smaller mass. And let's say r is the orbital radius. And so we want to apply Newton's second law here. So here, let's say that's our origin. So that's our radial direction is outward. Now let's apply Newton's second law to this planet here. So there's one force acting on this planet, and that is the force of gravity, which is inwards towards the center. And that's it. That's the only force acting on this planet. And so we can write down Newton's second law, F equals ma, where we have the force is inwards. We have minus g times the mass of the planet divided by the distance between them, which is r. And that's equal to mass times the acceleration, which is minus v squared over r. So we've got minus signs on both sides, which we can ignore. But yeah, we'll still just keep writing them down. Okay, now what about the velocity of a planet? Now, if an object is moving in a circular orbit, it's going to be moving at a constant speed v. And we define the period to be how long it takes to complete one orbit. So we go around, one time. Basically, for Earth, t would be a year. There's t in that equation. The period is 1 year for the Earth. But anyways, just speed is distance over time. So after one cycle, we've got a distance 2 pi r or a distance 2 pi r in a time equal to 1 period. So that would be v. So what we get is this equation. We can clean it up a little bit by crossing off this m. And we can also multiply by, let's multiply by r squared and get rid of this minus 1. So we have gm is equal to r v squared. So this is what we get by applying Newton's second law to the mass, like a sun and a planet. Now I should point out, because in the practice problems in the back, I put one challenging problem if you want to go a little deeper than what we need to in this class. But if you want to challenge yourself, I consider, if you look at the stars in the universe, it seems like about half of them are actually binary systems, where you have two stars orbiting around each other. And that's a very different situation than a very massive object with a much smaller object. So if we have two stars orbiting around each other, in the problem I said, let's give them equal masses. Say they both have a mass m, then the center of mass is right in the middle, and so they're both going to orbit like this, basically in the same circle. And if you want to do this problem, you have to be a little careful writing down this equation. This equation would actually be wrong if we applied it to a system like this. And the reason why, on the left side, this r is, this is the force of gravity between two objects, where r is the distance between them. So let's say we call the orbital radius little r, then the distance between them would be 2r. So the force of gravity would look like this. Now, the acceleration is v squared over r, where r would be the orbital radius, or the radius of the circle. And so, yeah, we get a very different result here. Basically, if we had two equal massed objects orbiting around their common center of mass, we'd have to replace this r with a 2r. Or in general, you could figure out what number to put there. So, yeah, just if you want to do that challenging problem, this is kind of how you would start it. And then follow the rest of it here. But for anything in our solar system, this works just fine. We can clean it up a little bit. And now you might be wondering, what is the purpose of this? And there's actually a few things. This is actually a very important equation, but we're not quite done. Because if you look at, say, a distant planet, like look at Mars, for example. What do we know about Mars? Do we know how fast Mars is moving? Well, yeah, we do, but at this point, you know, if you're like an ancient astronomer, you know, previous to Newton, you would have no idea how fast Mars is moving. And so, but we do know the period of Mars. We know the ancient astronomers knew the period of every planet that they could observe. And so let's replace this v with 2 pi r over t. So, well, we have, if we square that, we'd have 4 pi squared r squared over t squared. And let's write this, let's just clean this up a little bit. We have g times big M equals 4 pi squared r cubed over t squared. And I'm going to put a box around this. This is, could be written in, you could rearrange things a little bit, but basically, essentially, what we have here is an extremely important equation. This is one of Kepler's laws. Remember I talked about Kepler, how he, just based on observations, he kind of inherited this observational data about planets and stars, and he created his laws of motions without explaining why things acted the way they did. It was more just an observational kind of law. And one of those was that planetary orbits are elliptical, but the other one he figured out is that r cubed over t squared is a constant. And that's basically what we have here. Because if we just divide this equation by 4 pi squared, what we have is r cubed over t squared is gm over 4 pi squared, which is a constant for anything in our solar system. You know, this would be the mass of the sun. G is a universal constant. And so essentially what we have here is Kepler's law. And we'll talk about why that's so important. But before that, let's just do one little algebraic thing. Let's divide by big G. And then we can say M is equal to 4 pi squared r cubed over big G times t squared. Okay. Now let's say that we know remember r is the orbital radius. So let's say we know what the orbital radius of the Earth is, which we do, although if we kind of go back in time to when Newton was figuring this stuff out, we did not know what r was. But say we did, basically what we've done here is we've determined the mass of the sun. If we plug in r, we know t is 1 year, and so if we plug in r in meters and t in seconds, we'll get the mass of sun in kilograms. And this is a very general procedure. When you have a light object orbiting a more massive object, you can determine the mass of the more massive object just by looking at the orbital radius and the period and plugging those in this equation. So again, Galileo discovered moons around Jupiter. That was a really big deal at the time because they thought everything orbited the Earth, and showing that moons orbit around a different object, that was actually a huge thing at the time. But again, just by observing the moons, you could even take a picture of you could have say Jupiter and look at one of its moons, and you can determine the distance between them just because you know the size of your field of view. And so once you determine the distance you get r, and just by repeated observations, over a long period of time, you can determine the period, and so we know the mass of Jupiter. This is basically how we know the masses of objects and that we can't directly access just by watching things orbit them. Now, we would probably want to be a little bit careful applying this to the Earth because we know the moon is orbiting the Earth, and so we can use that to determine the mass of the Earth. One little problem, though, is our moon is enormous compared to... it's not the biggest moon in the solar system, but if you look at the size of the moon compared to the planet that it's orbiting, we have by far the biggest. So I think there's like a bigger moon orbiting Jupiter, but Jupiter is so enormous that, the moon seems tiny in comparison. But you could consider Earth to almost be like a binary planet, so like two planets orbiting around each other. Earth is a lot bigger, but still, we have a very large moon. So we'd probably want to be a little more careful if we wanted to accurately determine the mass of... Now this would actually work fairly well, but there could be a slight error at least by not taking the center of mass into account. But yeah, this is a very important tool for astronomers. You can look at planetary orbits and determine the mass of the objects. So that's a big deal. But I want to kind of a more immediate application of Kepler's law. Back then, I have a table in the book, which I don't have with me at the moment, but I'm going to just write down Kepler's law. I'm going to write it down the way Kepler wrote it down. R cubed over t squared is constant. Now, what they knew back in ancient times, we have Mercury, Venus, Earth, Mars, Jupiter, and Saturn. That's all they knew about back then, because those are all very visible planets. Actually, I've never seen Mercury myself. I would like to see it one day, but it's hard to see Mercury because it's so close to the sun that you can only see it, right after the sun goes down or right before the sun comes up in the morning. So you have to get the timing right, and then it'll always be close to the horizon. So you need a good viewing location as well, because trees or houses or whatever can block your view. So it's sometimes hard to see things on the horizon. But yeah, Mercury is definitely visible if you just know where to look and look at the right time and have a good spot. But anyways, what we knew is the period. Let's say the period in years. So for Earth, we have 1. Now what Kepler did not know is the radius. He didn't know the orbital radius of anything, but they knew the periods, and you could kind of put together a picture of the solar system. Like say, here's the sun, and here's Mercury, and then Venus, Earth, there's a little bit of a bigger gap for Mars. And then there's a pretty big gap where we have Jupiter and then Saturn way out there. So Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Usually the planets don't line up so nicely like this. Although I remember it did happen once, where all the visible planets lined up almost perfectly. And a lot of people freaked out, thinking that was going to be the end of the world or something, but yeah, we were fine. But anyways, they had some kind of picture like this. They knew Mercury, they knew the order of the planets, just in terms of increasing orbital radius. So we could kind of create this model of the solar system. But what about the radius? we had no idea how far away a planet was from the sun. Like Earth, the distance from the Earth to the sun, we had no idea. So what they did is they invented something called an astronomical unit, which by definition, an astronomical unit is the distance between the Earth and the sun. So that's one astronomical unit. And so we can just put this in here as a 1. In those units, that is correct. So if we measure the period in years and the astronomical unit, or the radius in astronomical units, this equation becomes r cubed over t squared equals 1. And so if we or r cubed equals t squared, or r equals t to the 2/3 power. So again, this only works if your period is in years. This will give you the radius in astronomical units. And so what they were able to do is create a scale model of our solar system. Now again, I forgot to bring my notebook with me, or the book, which, we have a table where we know the period of everything, and so then we can just plug that into the equation and get the orbital radius in astronomical units. And so that allows us, what Kepler's Law allows us to create a scale model of the solar system. And Earth is about 1 astronomical unit. I believe Mars is about 1.5. I don't have it with me, so I can't say exactly. But Mars is around 1.5 astronomical units. Just by observing its period, plugging it in, there we go. And so this allows us to make this scale model. We know the relative distances. But we still don't know what r is at this point. And so we don't really know the size of our solar system. But, we know the relative distances to everything. But this actually helped us find the size of our solar system as well. And that happened not too long after Newton was around. I think it was still in the 1600s. So Newton might have even been still alive when this happened. I think he was. But what happened is, pretty sure his name was Cassini. There was an astronomer who actually measured the distance between the Earth and Mars. So he was able to measure this distance in meters. Now, how can you measure distances in space? The basic idea is using something called a parallax. And the idea behind a parallax, you can do this very easily if you just have like a pencil. Just hold up a pencil, kind of close to your face, but don't focus on it. If you focus on it, you just see, like in this case, if I focus on it, I see a marker. But if I look at something beyond it, I see 2 markers. Like each eye is seeing 1. And like if you close one eye, marker, here, we can draw this. Let's say this is one eye, and this is the other. And say this is like the wall. So if an object is here, if you look at it from, say, your right eye, if you look at like where it would kind of match up with a point on the wall, it would be over there. With your left eye, it would look like it's over here. And so, that's why you can see, too, if you're not focusing on it. If you close one eye and then look at the other, you can see the object kind of bouncing around just because you're changing your perspective. And if you move the marker farther apart, these 2 images get closer together. So if you look at, let's say, a different point that's farther away, this, the difference is going to be a lot smaller. So we define like this something called a parallax angle. Now, angles are measured in degrees, and now we just use decimal points. But in the old days, they used degrees, and we still do this on a globe, to measure latitude and longitude. We can break degrees into minutes. Like 1 degree is 60 minutes, And each minute we can break up into 60 seconds. And so we measure something called the parallax angle. And again, because, as you get farther away, this angle gets smaller. And it turns out things in space tend to be very far apart. And so, you wouldn't want to measure the angle in degrees because that would be a huge parallax. Even though 1 degree isn't much of an angle. It turns out minutes are not even a good unit because they're too big. A good unit for measuring parallax is a second. Not like a second of time, but, breaking up a degree into minutes and seconds. And so there's a unit that comes from parallax seconds called the parsec. And so a parsec is basically the distance you get for, parallax angle of 1 second. Now, actually, I didn't give you enough information exactly. Now, how would we actually do this? Like, how could you measure the parallax angle to the moon? Well, Cassini didn't do it by looking at the moon and closing one eye and then closing the other. Another way you can improve the parallax angle is increase the distance, increase the difference in your, the two perspectives you're looking at. So your eyes, you have a few inches difference. You can notice a parallax for very close things. But if you look at something farther away, you need a much longer baseline to take these two observations. So what Cassini did is he studied Mars. And again, you can only do this at the right time of year when they're lined up. Like normally you could have Earth here and Mars could be over here. So that wouldn't work. Measuring the distance to Mars, that would give us that distance. But we want this direct. We need the Sun, Earth, and Mars to be, along the same line. And that happens periodically. And so in order to get 2 observation points, what Cassini did is he took a picture, or no, they didn't have cameras, but he took a measurement probably right after sunset. As soon as he could see Mars. And then he just waited. He probably took several measurements over the course of a night. But if you picture, here's Earth, and the Earth is rotating, and here's Mars. So if Cassini's over here, he's not going to see Mars because the Earth is in the way. But as the Earth orbits, he'll get to a point where he has a straight line shot to Mars. So you can get one measurement here, and then, again, you can keep taking measurements until you get maybe over here, where you have a straight line shot, but if you go past that, the Earth is in the way. And so again, the baseline that you can get to take your 2 observation points is equal to the diameter of the Earth. And, still the parallax angle is very small. Even if you use a baseline equal to the diameter of the Earth. But telescopes, they were still kind of a new invention. But they had come along far enough where he could make a direct measurement, measure this parallax between the Earth and Mars, and determine the actual distance between the Earth and Mars in meters. Now, this was the 1600s. I don't think they were using meters then. But, whatever units he measured in, we could, it doesn't matter. We could convert that to meters now. And so, again, I have the number in the notes. I forgot to bring that down. But the point is, now we know this distance in meters. And we also know this distance is around 0.5 astronomical units. Because from here to here is 1 astronomical unit. And from here to here is 1.5. So let's just say we have x meters. Then we have x meters equals, say, 0.5 astronomical units. And then if we multiply by 2, we get an astronomical unit in meters. And now we put the entire solar system together. And, because we know, again, using Kepler's law, knowing the periods, we can get the radius in astronomical units. And now that we know what 1 astronomical unit is, we can find the distance to all of the planets in the solar system. And so again, this was done in the 1600s, we had a scale model of the solar system and knew the distances. And just one more thing before we move on. I mentioned this parallax second is a convenient unit. And yeah, but what would you use for a base? Like, what if you want to look at distant stars? This method to look at Mars, that's not going to work. Just looking at Mars, you know, here and then waiting until, like, you know, sunrise and sunset, for example. Using that baseline as the diameter of the Earth, that's not even going to be close to being able to measure the distance to a star because they're very far away. And so we use a different baseline to measure the distance to stars. We can use this parallax method. And what we do is take pictures 6 months apart. So if you look at your orbit, like say you take a picture of a star here, and then 6 months later, you're on the other side. So basically, you're about, the baseline in that case is around 2 astronomical units. And if you use that as your baseline, you know, a parallax angle of 1 second, we call that a parsec. That's around 3.26 light years. So light year is just the distance that light travels in 1 year. So yeah, if you heard that term parsec, that's kind of short for parallax second. And using this method of parallax, we can determine the distance to the closer stars. That only works for closer stars, and we get better at it. Right now, we have a satellite that just does this, just measures, get very accurate measurements of the positions of stars, and the satellite only exists to measure parallaxes and determine distances to stars. But still, we're kind of limited because, again, it's hard to measure very small angles. And so it only works for stars that are relatively close to us. But this is the single most important method we have for measuring the distances to basically everything else in the universe. And the reason for that is we developed a lot of different methods for measuring the distances, like distances to distant stars or even distant galaxies. And it all fundamentally comes down to the parallax. So just to give you one example of that, there's a kind of star called the Cepheid Variable, which is a periodic star. And let's just say by looking at this star, they discovered a relation, like its brightness would go up and down with a certain period. And that period depends on how bright the star is. And as a general rule, if you know how bright an object actually is, and you can see, like, say you have an object that appears bright, something in the sky, like a planet. Planets appear brighter than stars usually. Of course, they're not. The reason they appear so bright is because they're very close to us, relatively speaking. So if you see a bright star, maybe it's because it's a very bright star, or maybe it's close to us. But if you know one, you can figure out the other. If you know how bright a star actually is, and then you can measure how bright it appears to be, you can determine the distance to the star. And there happen to be some Cepheid variables that are in range where we can use this parallax method. And that's how they were able to figure out the Cepheid variable method of measuring distances to stars. And so now if we see another Cepheid variable, they already have this method calibrated. And so that's one of the most useful ways of measuring distances in astronomy. These Cepheid variables. It's almost like these stars were designed for us to be able to measure the distance to them. Because they're very bright and they have that amazing property that it, by just observing them, you can tell something called their absolute luminosity, like how bright they actually are. And so they're, great method. But to calibrate that method, again, we had to have some in range to use this parsec, or parallax method to do so. So this idea is fundamental to knowing where things are, like how far things are, like how big are universe is, like how big our galaxy is by looking at distant stars or looking at distant galaxies. Okay, so yeah, I think that'll be it here. Now, I know I talked a little bit about parsecs or parallax. Again, that's not something that will be tested on, but it's an interesting topic and a very important application of what we just talked about. You know, as Keplers Law is putting together this scale model of the solar system. So that was very important, and also using it to determine masses of things by looking at their orbits. So that's what you really want to focus on studying. Now, erase the equation, but determining the mass of something just based on something orbiting it, and you know, just knowing Kepler's law that relates the orbital radius and the period of an object. All right, so that'll be all for this one.